Welcome back, boys and girls. Today we're going to be taking a look at constraint-oriented programming. It's not going to be everybody's cup of tea, but I just heard about it and I was like, what the heck is this? And I delved into researching this topic a little bit more, and it has to do with just a way that you approach solving problems. For example, pathfinding. If you want to find a path from one place to another, there are many possible variations of how you can walk there, drive there, etc. What's the most efficient one, and how do you find that most efficient path? That is basically the set of problems that constraint-oriented programming sets out to solve. I found this example really interesting, not really for the problem that it was solving, but really that once I was done with the initial example, I was like, yeah, this is what programming paradigms are about. It is about how we express our ideas in code. I just found this to be a very satisfying example. So without much to do, if you're enjoying the video, leave a like, subscribe. If you have any questions, make sure to leave in the comment section, and let's go ahead and get started. We are gonna be doing quite a simple problem. Here is a map of England, and we have a couple of cities. So we have Glasgow, Edinburgh, we have Manchester, Leeds, Sheffield, Bristol, and London. Some randomly picked cities, and what I'm going to do is I'm going to connect them using some lines. So Edinburgh is connected to Leeds, Manchester to Leeds, Leeds to Sheffield, Manchester to Sheffield, Manchester to Bristol, and then Sheffield to London, and Bristol to London. Now I'm going to pose a problem. I'm going to have three colors, let's say orange, yellow, and red, and I'm going to say, go ahead and place a color around the city such that there is no matching color in a connected city. So we cannot place orange over here, and we cannot place orange over here because then it's basically an orange connected line. We want a gradient. So you'd go ahead, place red or yellow there, green, and then another orange over here. And then let's say yellow over here, and then a green over here, and another orange over here. Not a hard problem at all. I just solved it in 2 seconds in front of you, but this is meant to illustrate an example that constraint-oriented programming is meant to solve for you. As you can imagine, there are multiple possibilities for how you can place these circles. Things like, for example, solving Sudoku can be done using constraint-oriented programming. And here in code, I have essentially outlined the same map. And what we will also go over is some terminology like variables, domain, and constraints. So let's come back to the map. I'm going to clear the drawing, and we're going to start off from the beginning. So we had these cities. These are variables. We then have the domains, which are the individual colors. Why is it called a domain? I'm not entirely sure, but that's just what it is. Sometimes these can be numbers, booleans. It's a set of values that can be assigned to a variable. And then we have constraints. So constraints is, more of a function type of thing, which says, okay, given these values and these domains, this has to basically, is the constraint satisfied or not, okay? So starting off slow, we have the variables. Let's go ahead and type them out. And because I have them already typed out over here, what I'm gonna have is a list of strings. These are my variables. I can use the constraint-oriented name for this, or otherwise I can basically call these cities. So a new list and fill out the values. And here we have the individual cities. Now for the domain, we are gonna need colors, which are going to be, let's say, rather than orange, yellow, and green, that's a little bit random. Let's go with RGB. So public enum colors, or let's say color. And we'll just go with red, green, and blue. Because this is effectively a type definition, what I'm actually going to do is take this out into its own file over there and let it sit there. So close this file. And to set up the domain, what you effectively want to say is, look, for a variable, this is the set of domain values that you can hold. So it's really a dictionary, and I'm going to be using an immutable dictionary for this, a reason why I will highlight a little bit later. But for a variable, we want possible domain values, and this is going to be color. We're going to create an empty from the beginning. I'll just call this domain. We'll then loop over all of our cities and initialize this domain. So for each city on the domain, let's go ahead and add under the city a new list of colors. And actually we'll probably want to get values out of color and just to list this. Okay. Since this is an immutable dictionary, we will actually just want to reassign it to the original dictionary over here. Okay, so these are really the things that you need for the base setup. So the individual cities, the colors that they can hold, they can have all of their colors. And if you're wondering about why would one city want one color but not another color, if you want to simulate that kind of behavior, you can think of a street where you can actually only drive one way instead of both ways. So just like all streets aren't equal, the values in terms of what domain values they can hold aren't going to be equal either. And that is primarily going to affect the constraint and mainly the logic within the constraint. So the setup was very easy to put together, but then what's the actual meat of the algorithm that we're going to be building over here? How do we find what colors we want to assign over here? So to kind of outline the idea, I don't know why I'm going to be drawing over the map. It has nothing to do with it. But let's say we have a tree of decisions. We're going to start from the top, and we're going to say we're going to start with Glasgow, and we might potentially try to color it red. We'll then try to color it green, and then we're going to try to color it, what's the third color? Blue. So if we start with Glasgow and we first color it blue, we're then going to go to Edinburgh and we're going to again try to color it in 3 different ways. If we haven't found anything good over here or a solution down this path, then we're going to try to start coloring Glasgow with green rather than red, and then we're going to go down this decision tree. Okay, so what we're effectively going to be building up is an algorithm that is going to construct a tree for all possible results, and then we can find a solution that is going to match all of our constraints. Whether we want to find one or multiple, I'm going to skip the multiple. I'm just going to say, look, I just want the one individual solution once all of the constraints are matched. So for the main tree traversal algorithm, we're going to first create a class, and this is going to be constraint satisfaction. Give this a body, and the thing that we're going to be passing in here are types of value and types of domain. Okay, in the constructor we will accept a list of our t value. These are going to be values, and the second thing is going to be this dictionary of domains. So instead of color, we're gonna choose domain or t domain, and these are going to be the individual domains. We will then initialize a field for the values, and we are going to initialize the field for the domains against the values that we're going to have. So Glasgow, Edinburgh, and let's say Manchester over here, we have a constraint that says the color between these 2 places has to be different, and the color between these 2 places has to be different. So Glasgow is affected by 2 constraints. So this is the second one, and let's say that this is the first one. And then if we're looking at Edinburgh, it is affected by constraint number 2 and constraint number 3. So we actually want to define 3 constraints, and these individual constraints are going to be objects. Once we're defining these constraints have to be added to this constraint satisfaction class. Okay, so public void add constraint. Let's go ahead and make this an empty method. To the add constraint method, we are going to be adding constraints. However, we don't have those yet. So for this, we are going to create an abstract class, as this is going to hold some information for all of the constraints. So let's go ahead and name this constraint. We're going to have the same generic parameters over here. Open this up, and in the constructor, we are going to say which values are going to be affected by the constraint. Okay, or sorry, not values, rather variables. So a list of t value, these are variables, and we can have them actually as properties. Go ahead, put them down here. The constraint can then be either satisfied or not. So for example, if the colors in Glasgow and Edinburgh are different, the constraint is satisfied, good. If it's not satisfied, that means the constraint problem isn't solved. We need to keep traversing the tree, okay? The logic for whether the constraint is going to be satisfied or not is going to depend on the constraint that we're going to be implementing. So this is going to be an abstract Boolean satisfied. Give this a body, or sorry, it's abstract, don't give this a body. And the parameter that goes in here doesn't actually exist yet. So let me just put 2 dots over here. We're going to take this constraint type, supply it over here. This is going to be the individual constraint. And now we actually want to go ahead and record these constraints. For this, I'm going to create another dictionary. These are going to be constraints. The constraints over here under a variable. So for example, again, if we have Glasgow or Edinburgh, we have a constraint. The constraint belongs to both of them. So once we're adding a constraint for all of the variables that we have, we want to go ahead and say that this is a variable. And actually, I'm saying now the strings over here shouldn't be strings. They should actually be t values. I'll put another t value over here. If we're getting a nullability warning, we can always say that t value is not null. Apply that constraint. We're then going to take the constraints that we have over here. We're going to try get value for this variable var variable constraints. Give this an if statement, and now we have a body. So from the beginning, this is not going to be initialized, and we don't want to hold domain objects, but rather a list of constraints for that value. So we have the variable constraints. Let's go ahead and just add the constraint that is being supplied. Also, in the constructor, we are going to initialize these constraints. So for all of the values that we have, let's go ahead, go to the constraints, not the values, the constraints. We're going to go ahead and under the value add a new list. Okay, and that is going to be ready to use over here. Also actually have to, initialize it properly. So constraints equals empty, semicolon on the end here, and there we go. Okay, so the initial setup on the constraint satisfaction, where again, we're just finding a place to compose all of this stuff together, and then the individual abstract class for the individual constraint. Okay, so let's make this protected. Let's move this out, and we're gonna go to program CS, and we're gonna take the constraint satisfaction, and we're going to move this out as well. I'm gonna have a squiggly over here because we haven't actually placed anything in here. And what is actually meant to go in here is the progress, the overall current result. So for example, if we are in a situation like this, I'm not going to color in all the red circles. Let's say we are going to have these 2 circles colored, or let's actually color them the same color, just to kind of emphasize that it's incorrect. We're going to say, okay, Glasgow and Edinburgh are both orange. Is this constraint satisfied or not? And because we're going to have a list of constraints, all of those constraints are going to check, is this satisfied, etc. This should not be satisfied. So the current condition isn't valid. Let's go ahead, clear the drawing, and the only thing that we've seen is key value pairs. So it's the end result. It's no longer what values a variable can hold. So back to the constraint satisfaction, we're going to just grab the immutable dictionary. We're going to grab about yay much, come back over here, place this here, and we're just going to remove the list, right? So it's just a key value assignment over here. We're going to import the immutable dictionary. This is going to be the state. The t value is again complaining that it could potentially be null. So we're not null. And there we have it. So coming back to program CS, we still don't have our constraints. What should this actually look like? Well, for our constraint satisfaction, so var cs equals new constraint satisfaction, where the variables are strings and the domain are colors. We're going to pass our cities, and we're going to pass our domain as well. What we want is we want to add a new constraint, our my constraint, and we want to say, look, we're doing this for Glasgow and Edinburgh. These cities are connected. There should be a constraint between them. There's also one between Glasgow and Manchester. So let's copy this. We're going to have Manchester over here. And then there should be one between Edinburgh and Leeds. So let's place Leeds over here. There will also be one between Manchester and Leeds. So let's grab Leeds and place it over here. So Leeds and Manchester, that's the line over here. We're then going to have Leeds and Sheffield and Manchester and Sheffield. So let's grab Sheffield, place this over here and over here. Okay. So these are, this is this line over here, and for Leeds and Sheffield, this line. And then we just have Bristol and London. Both of them are going to connect to Sheffield. So Bristol over here, London over here. And then between Bristol and London as well. So let's take Bristol and place it over here. So here are all the values that we have, and they have their own domains. All right, we have already seeded all of that logic. We now want to apply our constraint. Our constraint is that of colors. So let's go ahead and create city color constraint. Let's inherit from constraint. We're going to be a string and color. Let's go ahead, place this over here. Implement missing members, the constructor, and the satisfied bit over here. List of string variables. I haven't specified them as a string, rather an array, or rather, basically, if I put params, a string, square braces over here, and spell params correctly, we're just going to get the variables, and this should work just fine. Also spell constraint correctly. Let's grab the class name, place it over here, replace all of these. The only thing that you need to do here is actually to list this. How do we satisfy this constraint? We have Glasgow, we have Edinburgh, and we have the overall state. The constraint, speaking generically, should be satisfied if for all of the variables that we have over here, and maybe these shouldn't be an array, but rather first place and second place, but we can get those by array position. Let's say var place 1. This is going to be variables and then 0 over here, and then we're going to have place 2 and 1 over here. So we have the 2 places. Where are these 2 places within the state, right? So we'll have place 1 over here. And this is going to return us a color. This is the current state. So if Glasgow is currently painted orange, if it's not the same, let me copy this over here, as place 2, that means the constraint is satisfied. Otherwise, if this is orange, they're not equal, and this is going to return false. So then we should keep traversing. If we haven't traversed the tree far enough, what could happen is our state is just going to be empty. So let's say that if state contains key place 1, and this is going to be a not, copy this, or we don't have the place 2, we actually counterintuitively want to say that, yeah, the constraint is satisfied, because if we don't have enough state, that means we're somewhere at the beginning of the tree and we haven't actually went that far as to actually check all of those variables. So we're going to say, okay, constraint passing, keep moving. And then once we actually have enough information, we can say if these constraints are going to be satisfied or not. The actual algorithm for traversal is not yet here. That is going to go into this class over here. And that is going to take care of ensuring that we're actually covering all of the variables, okay? But for now, this is the implementation of our city color constraint. Let's go ahead and move this into its own file, all right? Come back to program CS, and there we have it. So the constraint setup, well, it's kind of the same thing. Now what we actually want to do is go ahead and solve it, all right? Create the method. We are going to return the final state. So the final state we already used in the constraint, which is just going to be mutable dictionary t value t domain. So I'll come back to constraint satisfaction. That is what we're going to return. And if we don't find anything, it's going to be nullable. As these things generally go, you want to just create a private internal solve. Here we're going to pass the initial state, or let's actually rather call this state. This is just going to evaluate to solve. Place this over here, create an empty, semicolon, And there we have it. Now we can just focus on this. So what do we actually do over here? So as I said, the way that you actually align on this is that you actually try to solve it is that you have a tree and you want to go ahead and try to traverse this tree and try to figure out all possible possibilities or all variations and see which one of those variations actually match the constraints that we have supplied. So to check if a constraint is being satisfied or not, the call for that will have to happen over here. The check that we're going over all of the variables will have to happen over here. And then the implementation for how you actually want to traverse the tree, depth first, breadth first, etc. That's just going to depend on the individual implementation. Okay, so perhaps what we're going to do is we're reaching Glasgow over here. We don't want to have Glasgow in one of our next nodes. So let's start there. We're gonna have all of the values. I'm not sure why they're called values. Variables is what they should be. Rename the constructor parameter as well. So let's go ahead, find the first variable that we haven't actually solved for already. So state contains key x, and this should be a not, semicolon on the end. Let's say that this is our variable that we're currently trying to solve. And I'm not sure why I have a find over there. It should just be a first. Once we have this city that we're looking at, let's go ahead and go to our domain. All of the possible variables, or sorry, values that we have for the variable, let's go ahead and try to apply it to this node. So on the state, we are going to set an item. If you've never worked with an immutable dictionary, that is basically how you want to do it. So we set an item under a key. The key is going to be the variable, and we set the domain. So this is effectively the current attempt and the whole reason why we're using an immutable dictionary. Let's go ahead and store this as local state over here. If this attempt is going to be the wrong attempt, we don't need to manage any new dictionary, etc. This is a whole different dictionary compared to this one. We can always go back no matter how far deep we're into the tree or how shallow, it doesn't matter. We're always working with a dictionary that we know isn't going to be affected depending on what happened at which level of this traversal. And this is why immutability partly is so amazing. If we want to do this in parallel, that is going to be even better. Okay, so we have the local state. We have effectively gone ahead, drawn the circle and painted a certain color. Now that we have effectively changed the variable, let's go ahead and check the constraints, right? Is the current picture correct? If it's not, let's move on to the next. And that's pretty much the process that's going to be here from here on out. So if, again, satisfied, a function that we don't have yet, for a variable, we're going to reach and grab all of our constraints. We want to check it against the local state. Let's go ahead and create this method. It's going to be a boolean. We want to go to our constraints for this variable, and then for each constraint that we have over here, let's go ahead and check. Not sure why it went for that one, if it's satisfied. Okay. The actual thing that we're passing is the local state, and that's it. So we can actually make this a little bit shorter if we say constraints, all individual constraint satisfied against local state. Okay, that is the final result. Let's remove this code over here, and that's pretty much it. And actually, this is so small, I'm gonna say, look, we can actually put this over here, but let's say to promote good practice, I will leave this over here, right? So for whatever local state that we have managed to produce, let's check if it's satisfied against all of the other conditions. Let's go ahead and try to reapply the same solving mechanism for this local state. So we're going to try to solve it for this local state. This is going to produce some kind of result. If the result doesn't equal null, that means we have actually managed to solve it. Okay, if we've done all of this and we haven't solved it, that means, well, that we should return null over here. And this is pretty much it. This is the traversal mechanism. One thing that I'm actually forgetting over here is a check that we have actually satisfied all of the constraints, and we should actually return something, right? Because we're doing a recursive call over here. So how do we check it? Well, we have a count of variables. If the current count for the current state is the same, well, we have actually managed to reach correct state, okay? Because the last time we checked it, it was satisfied. We could potentially put this over here, although generally when you write recursive functions, the condition for successful exit is usually right at the top. So I'm gonna keep in line with that, and that's pretty much it. Let's come back over here. We're gonna solve it once this is solved. So this is gonna give us a solution, and then with the solution, we're gonna go for each. We're gonna have our key value pairs. Let's write this out to the console. So console write line. We're gonna have let's say some kind of index, actually just int I 0, or actually start with 1. We're gonna have I++ dot key and then value, and let's actually put a little bit of space over here. Looking at this would really like it actually if I could spit it out to the console like this, but this is gonna take some time, you know, when I'm lazy. Let's go ahead and just run it, and we'll do a little bit of a manual check. We have an exception, the constraint satisfaction key not found Glasgow. So I'm just gonna check what's happening on line 60. Of course, the key could not actually be populated at that point, so let's actually try get value for this variable. Now var constraints return, this is going to be our constraints if they're all present over here and satisfied. Otherwise, if there are no constraints, let's just go ahead and return true over here. Now, for why we actually didn't have constraints, this should have actually added it to the variable constraints that we're setting over here. And yeah, because this is again an immutable dictionary, we need to keep re-adding it. So let's take the constraints over here, reassign them, and hopefully that will solve the problem. Run the application again. And there we have it. So our algorithm has decided to start with Edinburgh, marked it green. So for this, let's come back to program.cs, and I'm just gonna basically do what it did. First, let's say the 3 reds. We have Leeds, Glasgow, and we have Bristol. Then let me find the green color. We actually have 3 greens. So Edinburgh, Manchester, and London. And then blue, we have just Sheffield. So that's Sheffield over here. And there we have it. There is the solution to the problem. So again, why did I decide to make the video? Mainly because of this, right? Big believer of this. I think everybody should be doing it for their specific domain. I know we have a lot of orientations, a lot of, what do you want to say, patterns, architectures, whatever, tons and tons of different terminology to describe different things. What you're going to have in your own domain, in your own software that you're building, you're going to have the important stuff, the stuff that should be at the front. It's going to be, in constraint-oriented programming, it's these variables, domains, and then the constraints. Constraint-oriented programming, you build your program out of constraints. I think once you understand your domain, you're going to understand with what true units you're dealing with, and you want to orientate your software around packing away the details for building up your program out of those units. And constraint-oriented programming, constraints are those units. Functional programming, functions, or object-oriented objects. Your specific domain, your specific software, maybe it's going to have your own units. The idea here is whatever detail it is that needs to facilitate you working with those units, go ahead, pack it away, and then you're effectively left with this. On that note, I think this is it for this video. Thank you very much for watching. Hopefully you've managed to sit through this and enjoy the video and get the idea. If you did, don't forget to leave a like and subscribe. If you have any questions, make sure to leave them in the comment section. I have a C# course that is out. If you would like to know C# as I do, I highly recommend you take a look at it. If you would like the source code for this video as well as all of my other videos, please come support me on Patreon. I will really appreciate it, and a very big and special thank you goes out to all of my Patreon supporters. You help me make these videos. As always, thank you for watching. Have a good day.